My name is Alan Haley, and I'm an electrical engineering major in the Renner Research Scholars Program. My research project was conducted under Dr. Mithat Kisisakoglu of the College of Electrical and Computer Engineering. My project is titled Experimentally Testing and Modeling of Lithium-Ion Battery Cell Operation. To begin, I would like to present you with the outline of my presentation. First, I will go over the objective, then I will go into some background in order to clear up any possibly confusing terminology. Then I will go into the methodology of my research, finally the resulting simulation, and then the conclusion. My objective is to characterize individual lithium-ion battery cells without having to completely charge and discharge them under various conditions, including discharge current and varied temperature. And then I will extrapolate how long the battery will last on a full charge based on the manufacturer ratings. Over the course of this semester, I have been performing discharges on various lithium-ion batteries in an effort to see how they will react under a variety of conditions. Before I continue, I would like to clear up any possibly confusing terminology. Battery characterization. This is the process of determining the characteristics of a battery without having to completely charge and discharge it under a variety of conditions. Energy density. This is the amount of energy per unit weight of the battery. Cutoff voltage. This is the lowest voltage that a battery can be discharged to without permanently altering it, based on the manufacturer ratings. And self-discharge rate. Batteries generate electricity due to their internal chemical reactions. Ideally, this would happen when the battery is connected to a powered device. However, when the battery is in storage or idle, these reactions continue to take place. Those internal reactions would then slowly reduce the amount of charge that the battery can hold. This phenomenon is known as self-discharge rate. Some other terminology I would like to clear up is a battery and a battery pack. In this presentation, a battery will be a single battery cell, and a battery pack will be multiple battery cells connected in series in order to achieve a desired total voltage. The image on screen before you shows a series of battery cells connected in series, increasing from 1 lithium-ion cell to 6 lithium-ion cells. Now, why would I choose lithium-ion batteries for this simulation model? Lithium-ion batteries are the best performing batteries on the commercial market with regards to their energy density and self-discharge rate. Also, they have the highest voltage of known rechargeable battery cells. This high voltage, or EMF, meaning electromotive force, corresponds to allowing us to kind of push more current for a given voltage, which increases the capacity for work and allows us to use more power. On screen before you shows the various voltages of lithium-ion battery cells and other rechargeable battery types. And the image before you shows the structure of a lithium-ion battery cell. I will now go over the methodology of my research. My procedure for discharging each battery was as follows. I fully charged each battery to its maximum voltage based on the manufacturer rating. I then selected 3 load currents for which I would discharge the battery, also based on the manufacturer ratings. I then chose 3 temperatures for each battery's discharge, those being the maximum operating temperature, the minimum operating temperature, and a baseline of 25 degrees Celsius. I then collected various data points. To better illustrate how I went about doing this, I want to show photos of my equipment used during this project. This first slide shows photos of the charger used during this project. This was used to fully charge each battery before each discharge test and to recharge it to a safe storage voltage after each discharge test. This slide shows photos of the computerized battery analyzer equipment. The photo in the bottom right-hand corner shows the main CBA unit. This was responsible for reporting voltage, temperature, and current back to the computer. It was also responsible for low current discharges. The photo in the top left is the CBA 500 watt amplifier. This was responsible for discharges greater than 15 amps. This slide shows the photo of the incubator used for simulating the environment for which the battery will be used. These are photos of the single cell batteries that were used during this test. These are 18650 lithium-ion Murata batteries. These photos are of the battery packs that were used during these tests. These are Luminaire batteries and Tatu batteries. Here's an example of a discharge graph that was reported by the CVA software. This left axis shows the decrease in voltage from the maximum charge voltage to the cutoff voltage based on the manufacturer ratings. The bottom axis shows the energy density over time measured in amp hours. And the right axis shows the temperature measured in Celsius. Temperature slightly increases based on the amount of current that's being given off, that's being discharged at. At higher temperatures, it gives off more heat. At lower discharge currents, it gives off less heat. That is what this gradual increase is over the time of the discharge. From these discharge tests, I gathered various data points. Those data points were as follows: the initial voltage, the voltage during the duration of the discharge test, the final voltage, the energy capacity measured in amp hours, the temperature measured in Celsius, and the discharge current, which was measured in amps and constant for the duration of each discharge test. This discharge data was then used to create a simulation, the lithium-ion battery simulation model. This simulation was designed using MATLAB Simulink. Now, I cannot run the simulation here in my presentation, but I will describe to you how it works. To begin, you enter the manufacturer ratings. Those would be the nominal voltage, the cutoff voltage, the maximum and minimum operating temperatures, and the discharge current, the maximum discharge current for which it can be discharged. I would then enter the current data on the battery. Those being the maximum voltage it would charge to, the temperature at which it will be discharged, and then the current at which I will be discharging it at. This simulation then models the battery without having to manually charge and discharge each battery under these variety of conditions. Before I conclude, I would like to acknowledge the limitations of this simulation model. In order to create a truly universal simulation model, you will need a team of electrical and chemical engineers in order to account for the various factors. Some of those factors are as follows: SEI layer growth, that is the solid electrolyte interphase layer. The growth of this layer contributes to the capacity fade of the battery by actively removing lithium from the system. Another factor will be lithium plating. This is the formation of metallic lithium around the electrodes. Those will be the positive and negative terminals of the battery. Now, additionally, due to the fact that the largest battery packs used during these discharges were 6-celled, battery packs beyond 6-celled would give inaccurate results for this simulation model. Extreme examples of that would be the Tesla Model 3 battery, which uses 96 groups of 31 of those individual 18650 battery cells. Another example of that would be the San Diego County Backup Energy Facility, which uses about 400,000 energy cells. Now, ways to expand upon this model in the future are as follows. You could add data from additional discharge tests in order to improve the accuracy, and you could have this model work in conjunction with a chemistry model that focuses on the battery's degradation factors. With that, I conclude my presentation. I would like to thank Dr. Mita Akisakoglu for allowing me to work in his laboratory, and I also like to thank Calvin Flack, one of the graduate students in the research lab, who is responsible for me fully understanding and being able to utilize the lab equipment. This is my bibliography slide. I now open the floor to questions.
How practical is this simulation for usage on drones or electric vehicles?
That's an interesting question. The 3 graduate students in my research lab are currently working on designing an electric vehicle charger. Additionally, we've also restarted a drone or UAV project. This simulation model allows us to use the batteries in the lab to test those drone or electric vehicle charger without having to worry about how the individual states of the batteries will affect their application.
Can you explain some of the limitations again?
Yes. The limitations for this simulation model are as follows. This model does not take into account the chemical degradation mechanisms of the battery. In addition, it does not take into account the certain performance mechanisms of the battery that can be improved upon with additional discharge tests.
So you mentioned the popularity of lithium-ion batteries in the commercial space. Are there batteries that maybe perform better than lithium-ion batteries that are not in commercial use, and if so, why don't we know about them, or what are their limitations, maybe that they're not popular yet?
That's a good question. Currently on the consumer market, lithium-ion batteries are the best performing batteries in regards to their energy density and self-discharge rate. But when I began doing this research, I looked into the background of it, and currently there's an Australian company called GMG, or Graphene Manufacturing Group. They've been developing an aluminum ion graphene battery that they claim has 3 times the lifetime of a lithium-ion battery and charges faster. In addition to that, as of Wednesday, they filed a global patent for that graphene aluminum ion battery.
Okay, well, thank you, Alan.